Good morning. This morning we're joined by Professor Pieter Fourie. He is CEO of Innovation for Life. Good morning, Pieter.
Good morning. Thank you, Professor Boyson.
So Pieter, let's start at the very beginning. Looking at your CV, you've taken quite a few turns in your life, but let's start with the engineering aspect. How did you decide to become an engineer? What got you into it?
I was always interested in, of course, in engineering, electronics, but I mean, this was now way back in the 60s and early 70s, and at that stage, you know, the first man landed on the moon, which excited me. The first heart transplant was done, which was extremely exciting. And at that stage, we were talking about one day having computers that would would have in our hands, etc. So that was an exciting phase in the beginning of the electronic era, and of course of the transistor. So just after my matric, I was invited to apply for a bursary through the CSIR, and I decided, well, electronic engineering was something that was always exciting to me, and that's where it all started. So I started in 1971 as a first year at the University of 1972 as a first year at the University of Stellenbosch. And enjoyed it quite immensely, but at that stage already I was very attracted to medicine. So after completion, I spent 2 years working at the CSIR on computer-assisted design of microwave gun oscillators, which actually at that stage was extremely exciting, but I never thought that it would help me to eventually in my further research and development. And then after 2 years, I came back to the University of Stellenbosch, and then commenced with medicine, which I completed in 1984. And then I joined the university as a junior lecturer, and I met up with Professor Andre Kutsia, who was head of anesthesiology, and we talked about applying electronic engineering into medicine. So I helped him design. At that stage, we had to do everything. We had to write the software, we had to develop the analog to digital converters and build them ourselves. So everything was very brand new. And if we wanted to do statistics, we wrote the statistical programs ourselves as well. So it was extremely exciting. I had an Olivetti portable computer that had an amazing 468 kilobyte capacity. It was amazing. That was it, what we had. And we, of course, had stiffies and floppies, and that was the era of those at that stage. So that was a very exciting era. And in our research, because we were both involved in intensive care units, where we treated patients that was very critically ill. And we discovered, we knew that it was difficult to monitor the heart under these critical conditions, because taking a stethoscope or measuring blood pressure wasn't enough. So we decided that we would model the heart using an electrical analog. So we did that in an open animal model where we anesthetized the animal, pain-free anesthetics, of course, then did an open thoracotomy. We opened the chest, and then we would instrument the heart with sensors that you could then in 3 dimensions, so you could model the volume of the ventricle of the left heart pump, and measure the pressure. And I came upon a device in Houston where we could actually measure flow inside the aorta, so we could then accurately quantify the function of the heart under certain critical conditions. And that was eventually turned out to be my PhD. And I used an analog model, a transmission line analog model to model the heart, and then to check that I had to do the inverse Laplace transformations, which I never thought I would be able to do. But that was now for my PhD. And then Professor van der Walt, who was then head of engineering, the dean of engineering, he actually helped me from the electronics side and the modeling side, and the other professor from the medical side. So ended up actually demonstrating that the heart on the left side and the right side actually worked very much like a pumping system, and it actually is optimized, which all these amazing things, how wonderful the body is. And then on the critical conditions, there's an uncoupling of the heart from the load, and then we looked at medicine, how we could use medicine to optimize the function of the heart again under these critical conditions. And then I went into practice as well as a pediatrician. So half my day at the moment I spend working as a pediatrician, seeing patients. But again, that is a very, very valuable asset because it's hands-on, and you discover a number of needs in that field that you're working in. And of course, you can translate that then into an innovative concept which then potentially can be commercialized. In 2015, I came back to engineering faculty, and I became head of the Bioengineering Research Group, where we supported students, masters and PhD students, and I was there for 5 years, and we ended up about 55 students in a various array of expertise, from orthopedics, looking at structures and strengths and movement, and on the brain, where Professor Dawie van der Heever was sort of the expert, and I worked with him on looking at brain function and cognitive memory. So a lot of very interesting work that we did there, and then because we saw so many ideas that can be commercialized, but they ended up on the shelf. The idea was to start up a company that would work in close association with the University of Stellenbosch, license some of these ideas to the advantage of the university, and then commercialize them. So that's where Innovation for Life was born, and the idea to have, there's 3 sort of focus points. One is to commercialize innovative technology, and specifically for the need of 1 billion in Africa. And then the other is to support biomedical engineering students, because we lose a lot of students to Europe and to America and Canada and Australia. And the idea was to support them so that we can develop a core of excellence that in their own right they would end up in a company where they would also develop innovative technology. And then the third one was to have a social, be socially involved in the needs in our society. So those 3 core focus points is something that we aim at in Innovation for Life.
Fantastic. So many things that you've said there that I want to just touch on quickly. When you say Professor van der Walt, do you mean Pieter van der Walt?
Yes.
Oh, fantastic. He's also on one of our videos. He'll be going on soon. And then very interesting that you've gone through this process of bridging the gap between engineering and medical science, because one of our interviewees, Martin Weiss, actually said you often need an interpreter to go in between medical and engineering just because it's so vastly different. Could you maybe speak to that point and just say, obviously you must have had some skills that you could draw on from engineering that the medical guys were not able to draw from? What were the most important skills that you took from engineering?
I really believe that engineering sort of helps you to develop tools to look very a little bit more scientifically and more objectively at certain problems in the medical field, so that you will be in a position even to identify a problem that the physician is not even aware of. He's so accustomed to managing a patient in a specific way. He was taught this 20, 30 years ago. There's no other method, but you then see that there is really a problem, and you can actually point out that problem, and then of course identify the what we would call the user requirements around that specific problem. And out of the user requirements, of course, going through a specific program, you would end up in defining the engineering specifications, which then end up in designing the first prototype. So that's the advantage of being having an engineering background. But the other way around, I really believe it's very difficult for a physician to to understand the concepts of the mathematical background, or the software constraints or designs or mechanical constraints or electrical constraints. That to me is quite complex. So even if an engineer does not go the route that I would not follow the route that I followed by going all the way to become a physician, they have an immense capacity to contribute towards solving engineering problems in the medical field. I believe it's stated that in 10 to 15 years from now, 8 out of 10 engineers will be involved in some form of biomedical engineering, whether it's now developing a shoe that's more ergonomically, or whether it's now really invasive in a sort of artificial heart, or whether it's supporting from the outside computational formula to identify problems in the brain with MRIs or EEGs and so on. That's the big advantage that we as engineers definitely have, and can then support the medical fraternity.
Okay, that's actually a very nice segue into my final big question to you. Is many of the students that want to study biomedical engineering, or many of our students want to study biomedical engineering, what do you think are the most important things that they should look out for, or where do you think this is going in terms of skills that they should try to acquire when they study engineering?
The first thing is that going directly into biomedical engineering actually is a wonderful opportunity to there's a specific new field that is actually expanding rapidly. They need to understand the basic physiology and anatomy of the body. So they usually get taught that in the first year of their master's degree. But it's also something, engineers are usually in a very top level of intelligence, so they can actually self-learn as well. So you often find that they get involved in working with a company without the background in biomedical engineering, but they actually through self-learning become expertise. I've one colleague of mine who's now got a PhD in engineering. He's working in Germany with a company that's developing an artificial heart, and he's now the expert on the cardiovascular side, on the heart function side, purely because of his interest and his understanding of the dynamics. So you become an expert eventually. Fair enough, you will not do the operation yourself when you put an artificial heart in the body, but they need you as a partner, because you are intimately involved in understanding the dynamics, how it functions, how to optimize that. And now with machine learning and all the nanification of electronics and so on, it becomes excessively important to integrate engineering expertise in design and even in management and extracting information from patients.
Fantastic. Pieter, I'm afraid that's all we have time for. I really appreciate you giving up your time to spend with us, and I look forward to seeing your next degree on your CV. Thanks very much.
Thank you. I'm thinking about that, but that will be maybe before I'm 100. Thank you very much.